Hi everybody, welcome back to the channel. In this video we're going to be talking about maximums and minimums. And maximums and minimums are kind of a category that I throw in with talking about the domain and the range of a function, where a function is increasing and decreasing. Helps us understand a lot of different features about how a function behaves. Okay, you've actually probably dealt with maximums and minimums before in your past. Probably specifically when you're dealing with a graph that looks like this, and if you had quadratics back in your past at some point and say find the absolute maximum here, basically asking you to find the vertex. But if you had functions that are a little bit more complicated, it can be harder to find maximums and minimums. Probably the only way you did it in your past was to grab your calculator, which has a maximum and a minimum feature on it, and you might have used that to find maximums and minimums. Okay, so we're going to talk about two different kinds here in this video and kind of make a distinction about why do we need to talk about both of these different kinds. They're related to each other, but the first kind is called an absolute maximum or minimum. Some books use the word global. And an absolute maximum or minimum is the highest or the lowest point on the entire graph. We talk about this versus talking about something called a local maximum or minimum. And the idea of a local maximum or minimum would say something like this. Let's say that you have a graph here. Here's a local minimum. Even though it's not the absolute maximum, it's not the lowest point on the whole entire graph, because there's another point over here somewhere that's actually lower, but this is actually lower than all the other points around it. So we would probably draw a little circle around there and say, is it the lowest point in the circle, versus over here on the left, that point is the absolute maximum, not just a local maximum, but it's an absolute maximum. Okay, so again, you've probably seen these before, but you might say, well, what does this have to do with derivatives? Okay, I want you to look at both of these points that we have here and look at the tangent lines at that point. Okay, if you look at the tangent line at that point, you'll notice that both of those tangent lines are horizontal, and when you look at a horizontal line, the slope of a horizontal line is 0. And so another way to say that is that the derivative is equal to 0 for those values of x, or you could say for those values of, we'll call them c, I guess. So here we would say that f prime of c is equal to 0. Okay, this is going to be a common way that we find minimums and maximums, is to take a derivative and set that derivative equal to 0. Okay, but before we do that, I want to take a look at another kind of a graph or an example that reminds us that finding maximums and minimums is not quite that easy. It's not just one thing we need to watch out for. So here is another graph. Looks something like this. And let's see, this point right here is a local maximum, and not an absolute maximum, but it's a local maximum. And this point right down here is actually a local minimum. But if we talked about finding f prime of x, here we would say that at this one, for this value of c, f prime of c is equal to 0 up here, but down here we wouldn't say that. We would say that for this point right here, f prime of x, or maybe f prime of, give it a different letter, I guess, f prime of d or whatever you want to call it, f prime does not exist at that input value. So remember back when we talked about how do you know whether a derivative exists or not, there were two different characteristics that we needed. In order for a derivative to exist at a specific point, you needed the function to be continuous at that point, but you also needed it to be what we called smooth. And so smooth just meaning there's no sharp edges or sharp turns like that. Now that's a little bit of an informal language to talk about smooth, but you get the idea, no sharp edges there. Okay, so something we can think about is how do we find local maximums and local minimums. And by the way, we could talk about absolute maximums and absolute minimums, but absolute maximums and minimums are also just local max and mins. And so if you can find local mins, then you might have a chance of one of those local mins or local maxes being an absolute max or min as well. Okay, and so how do you find local minimums? There's kind of two criteria that we're going to use. In fact, these criteria both fall into kind of the category of something we call a critical value or also known as a critical number. Later on, we could talk about a critical point. The point is the xy coordinate. When we talk about the critical value or the critical number, this is talking about the x coordinate of the point that you're talking about. Okay, so how do you find critical values or critical numbers? Well, let's go back to our graph. We had two different cases. One case was where the derivative does not exist, and another case is where the derivative is equal to 0. So I tell you what, the first, the case where the derivative doesn't exist, we can kind of overlook that sometimes. I think so often I see students who just kind of forget about that case and only worry about where f prime is equal to 0. So I'm going to put that one first because I think it's a good one to just check, because otherwise we forget it. So the first situation is that we're going to look for where is f prime of c not exist. Okay, where does f prime of c not exist? And so what we want to do is we want to find c such that this happens. So find c such that f prime of c does not exist. The other one is find where is f prime of c equal to 0. Okay. Now here's how we're going to do this. Let's take a look at a quick example. Let's say we have something like f of x equals x to the third minus 3x squared plus 1. And we want to know, where does f have a local max and min? And that's assuming that it even does, right? We know that some functions don't even have local maximums and minimums. So it could be possible that this doesn't have a local maximum or a local minimum. We've seen functions like that. But what we're going to do is we're going to, first of all, kind of as a first step, find f prime of x. Okay, and then if we can look at f prime of x, remember from the last example, we want to see where does f prime of c not exist. So find f prime of x and look at number 1. In order to kind of answer the first question, we got to ask, what is the domain of f prime? Is there anywhere that f prime does not exist? If so, that is a critical value. That's a value for c where f prime of c does not exist. That's what we're looking for. So that could be a maximum or a minimum. Or the other way we could do it, the other thing we need to do is we need to say, where is f prime of x equal to 0? So we're going to actually find f prime of x and then look at the domain of f prime and also look at where f prime is equal to 0. So take a look at our function we have up at the top. Pretty easy to find f prime there. F prime is 3x squared minus 6x. Okay, so f prime of x is equal to 3x squared minus 6x. So we want to look at the first question, which was, where does f prime of x not exist, if anywhere? What is the domain of this? Okay, so the domain of this is all real numbers. So that means that f prime exists everywhere. So there's nowhere where the derivative does not exist. Now that's not going to be the case in every function, but that is the case in this function. Okay, so for number 1, f prime of x exists everywhere. Okay, so there are no critical values where f prime doesn't exist. Now for number 2, we want to set f prime of x equal to 0 and solve. So 3x squared minus 6x equals 0. Factor out a 3, or a 3x I should say, and you're left with an x minus 2. And so this is going to give you something like x equals 0 and x equals 2. And those are your critical values that could either be local maximums or local minimums. All right. Now, in order to tell whether they're local maximums or local minimums, I would recommend plugging in those values of x equals 0 and x equals 2 into the original function and find out which one gives you a higher value, an output value, and which one gives you a lower output value. And obviously the higher output value there is going to be the local maximum, and the lower one is going to give you the local minimum. Okay. If you had more than 2 values, you got to check them all and see which one gives you the highest value out of all of them. That's the local maximum. Which one gives you the highest value, or I should say that might have a chance of giving you the absolute maximum, and then you can test local minimums there as well. Okay. Now, that being said, this is dealing with local maximums and minimums. We could also look at absolute maximums and minimums, and there's actually going to be a third case for finding maximums and minimums, and it comes from an important result for us that we're going to see here, and it's going to show up again down the road as well. This is something called the extreme value theorem. Now, when you hear extreme value theorem, what I want you to think about is absolute maximums and minimums, not necessarily local, but absolute maximums and minimums. This is going to give us another way to be able to find possible values for absolute maximums and minimums, along with finding where the derivative doesn't exist and along with finding where the derivative is equal to 0. Here's what the extreme value theorem says. It says if f is continuous on a closed interval from a to b, then f attains or has an absolute max and min, both. Okay, so you might think about an example, because this isn't true for every function, right? If you say that, oh, not every function has an absolute maximum or a minimum, here's a good example function of that. Think about the tangent function, has vertical asymptotes. Okay, so you might say, well, there's no absolute maximum or minimum of the tangent function. Well, that's true, but that's because where the vertical asymptotes are, they create an open interval, not a closed interval, an open interval. So if we look at a function on a closed interval, like with what the extreme value theorem says, and if that function is continuous, there's no breaks or gaps or jumps, then f actually has to have an absolute maximum or a minimum. So how can you find maximums and minimums? We're going to see a few examples in the next video, but now we're adding kind of a third criteria, and so let me tell you before we look at the lay out those three criteria. Here's an example of a function. If we take our tangent function, and if I restrict that function to being on a closed interval from a to b, then here's what your graph is going to look like. I'm only going to talk about from this point to this point. None of the other points there really matter, so I actually don't care about what happens after B and before A. I only care about from A to B. Now look at where the maximum and the minimum are on this graph. Okay, the absolute maximum on the closed interval is at B. Again, we don't care about what happens after B. So the absolute maximum on the interval is at B, and the absolute minimum is at A. So that gives us a third way to talk about where could you possibly have maximums and minimums. Specifically, absolute maximums and minimums are on the endpoints of your intervals. Okay, so let's summarize a little bit, and then in the next video we'll see a few examples. So to find maximums and minimums of a function, there are three different ways we can think about this. So that says to find maximum minimums of f. Number one is, where is f prime of c not exist? What values are not in the domain of f prime? Okay, so to find that, you got to find f prime of x and think about the domain of f prime of x. Okay, the second way you can find maximums and minimums is to find where is f prime of c equal to 0. Okay, so find the derivative of f, then set that equal to 0 and solve for x, and you will find the values where you have those critical values or those critical numbers. Okay, now the third case is just for absolute maximums or minimums, is the endpoints of a closed interval. Okay, if you have your function defined on a closed interval, then you need to look at the endpoints of that closed interval and determine that, or think that those could also be maximums and minimums, even if you find critical points in somewhere else. Let's say you have a closed interval from a to b, and here's your function, and there are two critical points in here. If you take the derivative and set it equal to 0, you'll get those. But the absolute maximum might be up at here at B, and the absolute minimum might be here at A. You still have to check those endpoints as well. If you look at all three of these, you should be able to find any maximums and minimums of any function. Okay, hope you've enjoyed.